Welcome to CP1. This is topic 5. We're going to talk about binary search and meet in the middle. So we're going to illustrate the concept through examples as always. So the first example we look at is a LeetCode problem called the first bad version. So suppose we have n versions of software numbered 1 through n, and the one version here is bad, and whenever we have a bad version, all the versions following are bad. So we want to find out which version is the first bad version. And we are given a function we can call, which we can check whether a particular version is bad or not. So we can use this function to implement this find the first bad version. And the goal is to minimize the number of calls to the API. And n can be as large as 2 to the 31 minus 1. And the bad value is the number between a and n inclusive. So let's first do brute force sequential search. So the code is very simple. We start from 1. We keep incrementing I. We check whether I is bad. If the answer, if this return true, then we return I. But the first time we see a bad version, we're going to return I. So this will get time limit exceeded. Why? It's pretty obvious, because the problem specification says n can be as large as 2 to the 31 minus 1, so that's more than 10 to the 9, so that is too much for this kind of limited runtime. So it may take, it actually shouldn't take that long. It probably take 10 seconds tops, I would say. Well, maybe could be 30 seconds, but anyway, so this timeout. So we use a binary search, which each time we check the middle in the range and ask whether that one is bad. And if the middle one is bad, then we know the answer should be in the left side. So because we've already seen a bad version. And if the middle one is not bad, it's good, then we know the answer is in the right part, the right half. So that's the basic idea of binary search. I think all of you are familiar with it. But here we need to turn that idea into bug-free code, which is actually not trivial if you haven't written binary search a few times before. So so we maintain the two value, low and high, so the lower bound and upper bound. And also here our intention is the answer will be in low, high. So the answer we're looking for, the first bad version, will be in this range inclusive, and we want to maintain this invariance. So we will loop while low is less than high, and we compute the mid to be high plus low over 2. And this is our, we check whether the middle is bad. If it is bad, then we know the answer is in the left half. And we set high equal to middle. Otherwise, we set low equal to middle. And this actually gets TLE. And if you don't know why, I suggest you pause the video and think about it. So this is actually a fairly common bug when one writes binary search the first time, or maybe the first couple of times. It's important that this binary search loop must make progress. So here we have so that means after this once the execution, the new window must be smaller than the old window. If the new window is the same as the old window, then we run the risk of infinite loop. So we just keep executing with them. And here we run the risk of not making progress, because when high equals low plus 1, then the mid will equal to low, and then then if we are executing the else branch, means that the mid happen to be good, then we're not making any progress. So let's say if low is 1, high is 2, then mid is 1, and then the 1 is good, then we'll be keep assigning low to be mid. So then after the one loop, the low is still 1, high is still 2. So we just keep doing that forever. So the reason of the bug is that here I shouldn't be doing low equals middle, low equals mid, because if low is good and our invariance answer is in low high, then we know the answer cannot be mid. It has to be at least mid plus 1. So we can do low equals mid plus 1. So then that fixed this problem, and that's our second bad version of this using binary search to solve the first bad version. And it turns out that this still gets TLE, and I think this is less obvious. And if you don't know, I encourage you to pause the video and think a little bit. If you still don't know, I encourage you to read the problem specification very, very carefully and see whether you can figure it out. Okay, so let's look at the problem specification. So here, look at this value here. So n is up to 2 to the 31 minus 1. So that's the largest integer value that we can have. So when n is that big, when high start with n, and then when we add this to some value low, then we actually overflow. So this addition will result in a negative number. So when we're doing dividing by 2, this mid will become a negative number. So then from then on, things goes more or less haywire. So I actually don't quite know what's happening. All I know is I submit this code, it get TLE. So this we're basically all bets are off. It's kind of we get negative mid. We'll be querying negative mid. We don't know what we get back, and high and low, some of them will become negative value. So things will we don't know. We can't quite predict what's going to happen. So this is a little bit rare, this high low, because normally the range of this value are not that big, so you won't get the overflow. But actually for this problem it does. So that's actually make this a good example problem because it illustrates this kind of corner case problem. Okay, now let's fix that. So this is a third version, and as I said, it's still a bad version. So instead of doing high plus mid over 2, I first compute sort of high minus mid over 2, and then I subtract that value from high. And then this is guaranteed to be not overflow because no, actually this should be this doesn't make sense. It should be high minus low over 2. Let's see whether this code actually really also TLE. Okay. Oh, okay. It is okay. So the version I submitted is correct. So it's just that when I edited the slides, I didn't do the copy. I edited slides that got wrong. So this version still TLE. And again, this is not obvious unless you are really familiar with binary search. So I encourage you to think about it. And let's see why it is TLE. Actually, I want to type something here. So suppose n is 5 and our answer is 4. So 4 is the first bad version. So then let's just see what we get in the loop. So when we start, low is 1, high is 5, and then mid is 3. And 3 is good. No, let's make sure what is mid. Okay. So high minus low, so that's 5 minus 1, that's 4. 4 divided by 2, that's 2. So then, yes, mid is 3. So that is correct. So, and 3 is good. So then low will be mid plus 1. So low will become 4. And so that's progress. So high will become 5. And then let's compute the mid. So high minus low now is 5 minus 4. 1 divided by 2, that's 0. So mid equals high. So mid equals 5. And when mid equals 5, then 5 is bad. So then we set high equals mid. So then high remains 5. So then we run to infinite loop. So that's why this will get the TLE, because we are not making progress. And the reason is the way we compute mid here. So mid could equal high. And we could also set high to be equal to mid. Then that's a recipe for potential infinite loop. So when low is less than high, as we use that as a condition, we have to make sure, and we use this logic for update, we have to make sure mid can never equal high. Mid can equal low, because we never set the low to be equal to mid again. When we use mid to update low, it's mid plus 1. So we will be always making some progress. So that's the finally the good version we have. So we use low plus high minus low divided by 2. So in this, when high is low plus 1, this will get us mid will equal to low. But mid is always less than high. So that's important for this. So this is a correct version, because we are always making progress. Mid is guaranteed to be less than high and greater than equal to low. Whichever branch we go to, we are going to make some progress. So that's this problem.